Hello, welcome to our first trick, our first way of solving a differential equation. This is going to be about homogeneous differential equations. Quite a scary name, isn't it? Now, very much like in integration where you look at an integral and you already start thinking, maybe I do it by substitution or perhaps I do it by parts. This is a similar deal. You look at a differential equation and you're going to start to think, maybe I do it using the homogeneous differential equation technique. Or maybe I do the linear differential equation. Similar thing. Now, we're not going to have that many techniques, and this is just one of them. So, the homogeneous differential equations is going to be applied when I can't separate the variables, like we did last time, when I can't just take all the x's and dx's to one side and all the y's and dy's to the other. Now, this one here, you can't just do that. You can't have all the y's and dy on one side of the equation and all the x's and dx's on one side of the equation without exception. It's just not going to happen. I mean, try if you want. So how do you do this kind of situation? Well, here realize, and this is an important thing, pay attention now, is that I can actually write this as dy dx equals a fraction with y's and x's. If you can do that, if you can write dy over dx on one side of the equation alone equals a fraction with the y's and the x's, then you have a homogeneous differential equation. In other words, if you can write it in this way, and we're going to see exactly what do I mean by this way in a minute, but that's what you were looking for. When you can do this, you apply this trick. So how do I go from here to here? Let's take a look at that first. So these are the homogeneous differential equations, and that's what you have to keep in mind. There's something always dividing. So in this equation, if I take 4x minus 3y to the other side, I end up with this. Now I divide by this part here, and now I have the differential alone on one side of the equation. Now, how do I turn this into a function of y over x? All I have to do is factorize, and this is what you're going to end up with. If I factorize the x, I end up with this expression. Now, the x's cancel out, and hence I have my differential, the dy over dx, in terms of y over x. That's exactly what I needed. That's exactly what my definition was telling me to go for. So once I have this, I solve it. Now, how do I solve it? Let's take a look at it. Here's my equation, as we had it before. And this is the trick you do. You're going to do a substitution. Now, you're going to do the substitution in the following way. You're going to write y to be equal to v times x. Now, v is an expression that we don't really know maybe exactly what it is, but it's an expression, really it's just going to be y over x. It's not a constant, it's a variable, okay? Just think of it as a variable, not a constant, just like a y or the x. It's not a constant, very important. So you're just going to do the substitution. To be honest with you, once you do it, it's all going to work like a charm. It's important to know perhaps how to do it and do it a few times yourself. So if I just do the substitution straight away, or wherever I have the y, I put vx, of course the x's are going to cancel out, and I'm going to end up with this nicer expression. However, the important thing is that here I don't have a dv, so how am I supposed to solve this? The answer comes by simply saying, well, if y is equal to v times x, when I differentiate this thing, I'm going to end up with this thing here, right? Because the differentiation of y, that's y prime, it can also be written as dy over dx, and the differentiation of vx, since they're both variables, is going to be product rule, and hence I end up with this expression. So I can substitute that into my equation, and this is what I have now. Now I can take the v to the other side, and I have all the v's together. Right? I can even open it up if I want to. And now I can actually just separate the equations. Now at this point here, I can just do it like a separation equation. You see, now I have all the v's and dv's on one side of the equation, and all the x's and dx's on one side of the equation. And we can now proceed as usual. Now this example I chose actually turns out with a long integration I don't want to have to do. I'm not sure whether you're supposed to know how to do this. I think you should know how to do this, to be honest with you. Being high-level math student, you never know. But it's not going to be a nice integration. It's going to take me a long time, so I'm going to finish the process with a different example. Suppose I have to do this one here, another homogeneous differential equation. Again, if you try to separate the y's and the x's, you can't just do it. And here they can give me a specific solution, okay? So again, I write it in homogeneous form. How do I do that? I take the x's dividing, I factorize the x's, and now I have it with my f of 1 over x situation. And hence I can do my substitution now. Y equals vx. So of course dy over dx is equal to dv dx times x plus v. I make my substitution in the original equation. The x's cancel out. And I take the v to the other side. And hence I'm going to end up with this. Now this one I can integrate quite easily. It gives me natural logarithms. Great. Now remember the c. Don't disrespect the c. Now, important thing to deal with the c. Sometimes you might, because you see like everything here has a logarithm in it, except the stupid c. But since they're constants, I can just redefine them if I want to. And I can say, well, you know, 2c is just going to be natural logarithm of k, which is just another constant. Why not? I mean, you can do that if you want to. The important thing that you have to maintain is the relationship these constants have with the x's. So I can rewrite this like this, which allows me to end up solving my differential equation, getting rid of these logarithms, because I put these ones together, and hence I end up with this expressions here. Now, it's still not done. Yes, differential equations can take quite a lot of work. Again, I have this situation here. So I have to undo the substitution. You see, there's no differentials here anymore. I'm kind of done. I just have to make sure that I leave it with a y. So again, I just rewrite this to get rid of my equations. And to leave the y alone on one side of the equation, I'm going to have to take the 1 over to the other side, the minus 2 over to the other side, and the x multiplying. And I'm going to end up with my solution. Now, I have finished solving the differential equation. We realize how the k actually ended up being within x. Now, I could go back and say, well, you know, like with my previous substitution that I said that 2c was equal to natural logarithm of k, I can put it back in terms of c, but that doesn't matter. The important thing that has to be maintained is the fact that this constant ends up being in the denominator with an x. That's what's going to determine how the different curve solutions are. Now, they give me an actual point. They give me an actual point, so I can actually calculate the value of k. Now, this expression, and I know that this is the point here, so I just substituted it. For the x's, I put a 2, and for the y, I put 1/2, and hence I end up finding out that k is equal to 1/2. So I have the final particular solution of the equation. And this is an example of a long homogeneous differential equation. I'm sure you understand now why I didn't want to do the whole integration of that thing earlier on, because it does take quite a long time. Most of the time, the differential equations you'll have to do will not be that complicated, and if they are, it is because they come and belong to one of those long exercises worth many points with many different sections. So think about it, that there probably will be structure down for you. Like, do this little part, here's some points, then do this little part, here's some points. However, you need to know this process, so you're going to do some exercises on this.